Okay. So hello everyone. My name is Michele Guala. I'm a professor in the Department of Civil Environmental and Geoengineering and a faculty member here at SAFL. So thanks for coming on our biweekly seminar. It is my great pleasure to introduce Gokul Pathikonda. So Gokul is a fluid mechanician and an experimentalist, and is an assistant professor at the School for Engineering, Matter, Transport and Energy at Arizona State University. One thing interesting is that he graduated, got his PhD in 2017 with Ken Christensen at the glorious TAM, at the Directly Applied Mechanics Department at Urbana-Champaign. And Ken was a postdoc when I was visiting Ronald Adrian's lab. So he's the one who taught me how to do proper fluid mechanics experiments and how to learn PIV and so on. So there's a little bit of legacy coming in, and I'm very glad that we'll see that legacy, especially in the measurement that Gokul is taking, which is really advanced experimentation. So without further ado, Gokul, thanks for being here, and the floor is yours.
Okay, talk about our research work at Arizona State University. Been having really fruitful conversations since morning, so I'm excited to talk about these things. So at ASU, we have the Complex Mixing and Advanced Turbulence Laboratory. That's the name I came up with. And we studied turbulence and fundamental aspects of turbulence for various applications using experimental tools. Broadly speaking, we look at wall-bounded turbulence extensively, specifically high Reynolds number turbulent boundary layers. As you all probably already know, like it occurs for ships, airplanes, submarines, wind turbines, atmospheric processes. We also look at turbulence and multi-phase mixing. So mixing and turbulence is the other broad area of focus that we do at in our lab, specifically related to chemical industries and some geophysical phenomena. Right, and another big aspect that we're very keen on is diagnostic developments, more of integrating multiple diagnostics to get a much more complete picture of turbulence than any single diagnostic would be able to provide us. But for today, instead of going about all of those things, I'll focus on two specific aspects. The first one is scalar transport in turbulent boundary layers. Is this working? Yes, it's working, I think. Okay. Thank you for that. Okay. So we're going to look at scalar transport within turbulent boundary layers. This basically marries my PhD work with my postdoc work. The other topic that I'm going to broadly cover is separation over textured surfaces. So these could look like very different problems application-wise, but the problems scientifically come back to what happens within a high Reynolds number turbulent boundary layer. Okay, so again, I don't have to go through this in great detail because a lot of you here is already familiar. But just to establish nomenclature, and as is customary when we talk about a high Reynolds number boundary layer, here is an airplane. Right, and if we start with it, if we want to visualize this, we basically kind of overlaying water flows on top of an airfoil to give an idea on how a boundary layer would develop. So as you see, as the boundary layer goes further and further downstream, you get much wider range of turbulence flow structures. The boundary layer gets much thicker. So that basically is the essence of a high Reynolds number turbulent boundary layer. And the reason we want to characterize this is because we all live in those, in one of those, and these turbulent structures are essential for transporting pollutants, particulate matter, etc. The other big reason we like to study this is because these occur over airplanes, like I just shown, and we spend a ridiculous amounts of fluid to overcome the skin friction drag that comes and is modulated by a lot of these turbulent processes. Right. Again, quickly redefining what a high Reynolds number boundary layer is, so that we're all on the same page. This is a very nice demonstration that Nick Hutchins once from University of Melbourne once demonstrated. So we can define Reynolds number as the ratio of the largest to the smallest scales. And if we look at the airplane and kind of look at the boundary layer development as the Reynolds number, right? And then we like to look at it in a logarithmic scale, right? If we look at the log scale, one of the highest DNS, RE tau of 5,200, is probably somewhere on the nose of the airplane that we typically travel in, right? One of the highest high Reynolds number laboratory experiments, they pushed this by a few tens of thousands from here. So I'm talking about very well resolved turbulent boundary layers in a laboratory is somewhere in the cockpit, right? And if we look at like the Princeton super pipe, and they talk about very, very high Reynolds numbers within the laboratory, we're probably somewhere in the business class up there. So my coach class gives us very high Reynolds numbers, right? An atmospheric boundary layer is probably somewhere else, right? We know that it's probably of the order of 10 to the 6, right? The point that I'm trying to drive is most of our boundary layer are very high Reynolds numbers, but most of our laboratory research is not. And we heavily rely on the scaling laws to be able to bridge this gap, okay? And I quickly also want to talk about turbulence and coherent structures. So coherent structures, we can basically define them as motions that have finite temporal and spatial scales that can be described some way statistically, right? And the most important ones to kind of simplify is the near wall quasi-streamwise vortices and large and the very large scale motions that happen outside of a boundary layer, in the outer regions of a boundary layer. We would like to pretend that these are like Reynolds number independent and they're kind of fairly universal. At least we like to pretend that way, right? But what we are going to be focusing on is the large scale motions and the very large scale motions for our research, because these get stronger with Reynolds numbers, so they get more and more energetic, right? And they get a larger and larger hierarchies as we go with higher and higher Reynolds numbers. And they can be dominant producers of TK at high Reynolds numbers because of the hierarchy that they can occupy. Okay? And so if you're really looking at the high Reynolds number applications and the high Reynolds number processes, we really need to be mindful of what these large and very large scale motions are doing and their action on these things. So the theme of this talk is going to be basically, to phrase it formally, what is the role of the large scale coherent structures? First, in transporting and mixing a scalar plume, right? This goes back to the atmospheric boundary layers. And the second one is in initiating a boundary layer separation, right? And I'll talk about it in a little bit more, but the hypothesis we work with here is that these structures become really strong and they're very susceptible to the pressure forcing, and a separation initiation primarily happens when these outer large scale structures become stronger and stronger, right? But let's first talk about the first thing, and I want to refer to this as a scalar transport within a high Reynolds number turbulent boundary layer. As always, I get to talk, but the real work actually is done by my student Isaiah Wall. He just defended and successfully graduated like a month ago, right? And we can very easily see why a scalar transport in a high Reynolds number is important, because it's critical for pollutant transport if you want to model order nuisance in an urban environment, hazard analysis of accidental or intentional sources of hazardous materials, or source triangulation. So many of them are forward and inverse problems, easier listed than solved, right? But a good example of it is basically here. This is in Phoenix. That somebody took, and this is a fairly common phenomenon in Phoenix. In summers, it gets really hot, and something or the other catches fire, right? We actually have a dedicated subreddit for this that says Phoenix, what's burning, okay? It's like a forum that you go and you get beautiful pictures of things catching on fire, right? And if you see, you can see that there is a plume that raises, it's buoyant, so it raises a little bit, and then it kind of disperses, it kind of meanders around and disperses. right? And as good academicians, if you want to take all the reality out of this, right, we'll basically look at this plume that's injected at a source height, and it kind of meanders. We kind of refer to this as meandering of the center of the mass, and then it kind of relatively disperses. Right? And the question that we wanted to ask was, well, how do these coherent structures influence meandering and relative dispersions? Specifically to the extent of, like, if I need a short execution time model that scales very well and captures these high Reynolds number processes, what is the best way of doing this? So the thing that we want to study was that, and first thing that we did was basically dig through this and map out all the tools that we have at our disposal, right? And this is a fairly typical chart you will see, right? So on the horizontal axis, I have the Reynolds number, so which is basically the boundary layer complexity. And on the vertical axis, I have the turbulence and plume resolution that the different techniques can give. Obviously, the ones that can take us to very high Reynolds numbers have to have a closure assumption in there. So they will have very little turbulence and flow resolution. Then you can do field measurements with points, or we can do RAN simulations. There have been lab experimental measurements. Again, this is literature only on plume transport in a boundary layer. So this is a very specific classification of the literature, right? But if you look at the lab experimental or LES or DNS that look at the specific aspects of plume transport, right, they're typically limited to low Reynolds numbers. Right, so this kind of brings us to the problem of where we need high Reynolds numbers to observe where these coherent structures are dominant, right? And we need high spatial resolution, so you can actually resolve what these coherent structures are doing, both for momentum transport, which has been studied, and scalar transport, right? And if you look at the lab experimental flow field measurements itself, right, which is what we wanted to look at. I've kind of listed these things, but I kind of want you to focus on the fact that most of the structure resolving measurements have been done in water, and this is no accident because it's much easier to measure scalar flow fields in water. Fluorescence imaging is much easier in water, right? With an exception of one study, right? So all of the current literature is typically on the low Reynolds number side, right? Predominantly in water, which means the Schmidt number effects are very high. And I haven't stated it here. It's very hard to get very large density disparities in water. We cannot have fluids that are 3 times as dense and still be able to perform these optical diagnostics in water. So the first thing we wanted to do was, like, let's develop the diagnostics. Let's see if we can, using the more powerful lasers we have, the more sensitive cameras we have, if we can map out both scalar concentration and the turbulent velocity flow field within a boundary layer for a problem like this, right? And we'll do this for a passive scalar in air, so the Schmidt numbers is of the order 1, right? But the plan is eventually to kind of extend this to higher Reynolds numbers, where you actually get like a decade of logarithmic layer, like maybe a few hierarchies of the coherent flow structures, right? And do this in a slightly bigger wind tunnel. So the first goal was basically to do these things, which is what I'm going to focus on for this work. So we basically took a small wind tunnel that's much easier to work with than a very large wind tunnel. And then we have 2 cameras. So if you look at this, the configuration is this. The flow comes from left to right, and the boundary layer develops. And we basically have a very small injector. I mean, this is not to scale. The injector is very, very tiny. It's about 1.5 millimeters in a 25 millimeter boundary layer, the 25 millimeter thick boundary layer, right? And we inject acetone through this thing, right? And the beauty of acetone is it can absorb UV light and fluorescent blue light. So we can actually image this acetone plume, right? To image this, if I look at it from the top-down view, I basically have one camera that only images blue light, And then I have another camera that only images the scattered green light. So you actually have a PIV measurement on one side and planar laser-induced fluorescent measurements on the other side. So if you take the raw image of PLIF, this is kind of how it looks, about a boundary layer or so downstream from the injectant point, which is where we were interested the most for this problem. Getting a raw PLIF image is easier than actually converting this image into mixture fraction measurements, because calibration of PLIF for acetone imaging is extremely hard, which is kind of what we went about to do. I'm going to skip the boring steps in between, but if you do everything right and things work out reasonably well and the calibrations work out and you lay on top of each other, you get pretty images like this. So what I have here is I have a plume that's coming in. So this is the contours are mixture fractions going from 0 to 1 of the scalar plume. This starts about 1 delta downstream. I haven't put the axis here. And you get the velocity vectors on top of it. So you kind of see exactly how this is being transported at that snap, at that frame in time. This is, I believe, bandpass filter, so I kind of wanted to accentuate the turbulent structures. But you can kind of see that. If I take one more snapshot, you can see that you see the scalar flow fields and then the structures that kind of roll this scalar up. And wherever you have these low velocity stagnation points, sometimes you kind of get this scalar to kind of accumulate as well. But what is happening here is basically a plume that's being injected continuously. It's kind of being rolled up and kind of rolled up into different packets here. Okay. So we did 2 locations. So the first location was the logarithmically region injection. Sorry, I have to be clear here. So the injection is somewhere around here. So it's actually very close to the wall. The second injection is slightly further out, so you get similar structures. So we investigated this for 2 injection locations closer to the wall within the logarithmic region, further away from the wall for the wake region injection, though I'll mostly focus on the former. But before we do that, just to gain some confidence in making sure that we got the diagnostic right and it's actually quantitative, we took the mean concentration evolution and kind of compared this to the classic Gaussian plume spread model that basically says, given some turbulent single point statistics, how should the plume be spreading in space? This problem has been studied for about 40 years now, more than that. So we have well-tested formulations for such a simple configuration on this thing. And we did do that, and we compared the plume spread that we see with the plume spread that these models give. Basically, the solid line is the model, the blue line is what we see. So this is for the logarithmic region, and this is for the wake region injection. Obviously, we see that our plume spread is much closer to the analytical predictions for the log region injection compared to the wake region. We speculate a few things on why this thing is. One of them primarily being that these assume the point source to be much smaller than the boundary layer thickness than what we have here. Okay. But other than that, we get reasonably good agreement with what the plume spread should be and what we notice. Right? We also did more comparisons to other studies. So now we can actually do turbulent fluxes because we measure them simultaneously. So we get wall normal turbulence flux, and we compared it to the literature that have done this with single point measurements that measure both. And it agrees very well, actually, even in magnitude and trends to what was reported in the literature. We discretized the blobs. The reason we are interested in this is in this region between 1.5 delta to about 3 delta is because this is a region where you have very high intermittency. So you have a plume that comes in it breaks up into multiple discrete packets. So you get this very highly intermittent flow where you get high concentrations of the injected plume and very low concentrations of the ambient fluid simultaneously. So we looked at the spatial trends because now we could. So we could threshold it, and we kind of looked at, okay, what is the size distribution of these things? What is the orientation of these blobs for different injection conditions, so on and so forth. And then how does this blob evolve as we go further and further downstream? So we kind of had like a plume breakup model. I can get into more details with any of these things if you're interested in. But I wanted to go back to the motivation of our talk, because we set about doing all of these things because we wanted to learn what is the influence of the coherent structures, right? Again, just so that we're all on the same page, let's talk about how do we identify the coherent structures? How do we define this, right? And we define this with a coherent vortex packet. So if I ask you how many vortices you can spot, right? You can basically spot one vortex here, maybe a vortex there, maybe a vortex there, right? So this is like a snapshot in velocity of the vortices, right? So there is one there, one more there. I mean, if you squint your eye and try really hard, right? There is one more vortex there, and then I'll say there is one more vortex here, right? And the reason we don't see this is because it's actually moving at some velocity, right? So if I actually look at it in the local frame of reference, this vortex pops alive. So it looks like these two vortices are moving with certain velocity. These three are probably moving with a slightly slower velocity. So there are these groups of vortices that move together, which is what we call the coherent structure in the textbook case. That are kind of inclined at a certain angle, depending on the packet and how you draw them. These angles can have different values. Okay? But the reason I knew that these vortex heads were there was because I looked at the contours of what's called a swirling strength. Again, this is related to the eigenvalue of the velocity gradient tensor. Anytime I have a very high value of swirling strength, it basically tells me there is a swirling motion locally in some frame of reference. So this is frame invariant. And this is kind of how we identify these vortices and have traditionally identified these vortices. And none of this is new. I kind of just wanted to put this here so we're all on the same page, right? This is basically, this is a slice of this coherent vortex packet that many of you would have seen like hundreds of times now. But all I'm trying to say is I'm going to relate these vortex arrangement to my swirling strength field going forward to look at the scalar trends. So if I look at the scalar flow field on top of these coherent packets, a trend seems to kind of come alive, right? So I have a vortex packet, of a vortex head here, and then I have a blob of scalar here. I have another vortex head, and then there's a blob of scalar. And it's the same thing. And sometimes the vortex seems to kind of strain this out around the inclined shear layer, right? So this is a very, very strong trend. Then if I show you one more packet, you kind of see one more thing. So you get like another vortex head, a huge blob, a vortex head, like scalar blob, so on and so forth. So what we have is we have vortex heads that are inclined that we already knew. But what we see is that in this region where the plume is being stretched and strained in a highly intermittent fashion, we also see that the scalar also places itself between these vortex heads. So they're basically ripping apart this scalar plume in a very coherent fashion. So if you ask me the question on what is the role of large coherent structures in the plume meandering, dispersion, and breakup, so my answer from these observations would be that, okay, you have a strong preferential local arrangement of scalar relative to these coherent vortex heads, right? But if you are a turbulence researcher, you're going to question me. It's like, hey, I mean, you might probably pick two best looking figures and you're showing this to write this narrative, it's like, what's to say that this is a very dominant phenomenon, right? I mean, and you would be right. I did pick the two best looking pictures to demonstrate this process. Though my word, like if you take my word, it's not hard to find this at all, right? Like about every fourth figure that we saw kind of had this arrangement, right? And for this arrangement to happen, the coherent packet has to line up in a certain way with the injected plume. So it's not always this, but it's not hard to find this as well. And more specifically, we found this. So again, the injection is happening around 0.1. We found this anytime there is a high concentrated region far away from the injected location. So if you kind of keep looking at it, stare at it, for many, many days trying to find trends, you'll realize that like any time a plume reaches far away, you see this coherent arrangement. And that is almost one-to-one in my experience. Like anytime I see it, it gets there. That's what we set about doing. Like, can we show this in a statistically significant manner that this actually occurs every time a plume appears, right? I will skip the details of these things, but we basically take this approach of linear stochastic estimation, which is we estimate a conditional average to the first order as a kernel times your conditional event. And the kernel turns out to be a 2-point correlation for a scalar. And this is what was used to actually identify the coherent vortex packet. So for example, they basically picked a swirl event locally and looked at the direction of the velocity field, and they saw that there are coherent packets. There's this long distance coherence with like an inclined, like a shear layer that shows up. So this is how they said that, you know what, these coherent packets are also statistically significant, which is what we're going to use. So I'm going to ask two questions in the following slides. So I'm going to ask from my quantitative description, we're going to say, given a high concentration event away from the wall, what is the average concentration and the velocity fields? So again, I'm going to look at the average concentration and velocity fields given two conditional events. The first event is what I described. I said every time something is far away from the wall, you see this arrangement. And the second thing is it bidirectional? If every time I see a swirl event away from the wall, do I also see the correlation, right? And I'm going to use these blue dots to show the conditional event. So I'm going to look at wherever the blue dot means I'm using a large fluctuation of a quantity there, right? With that, let's look at that. So the first one is we went far downstream, went far away. Again, the injector is about like 0.1, and I believe we looked at it at like 0.28 something, right? The location of this does not matter. I can pick it anywhere in this neighborhood and I would have the same trend. So it's fairly robust to the choice of location. And I'm asking in this, what is the concentration field given a high concentration event far away from my injector? Right? And what you see is obviously I have a high concentration far away. That was my condition that I chose from. And I see a negative fluctuation of, so if I have high concentration here, there's a high probability that there is no scalar here because the plume basically meanders around here, right? But what was more interesting, we call this the primary blob. This is uninteresting, right? We actually see that there is a secondary blob that follows up, inclined slightly upstream, and much further upstream, you also see a very weak secondary blob. And like I said, regardless of where I choose this conditional event, I usually get the same behavior, right? We didn't want to believe it, so I'm not going to show this, but if I choose a low concentration event here, say, okay, you know what, this agrees. So if I estimate the concentration field with a low concentration event here, right? Then I get a red blob here, I get a big blue blob here, so deficit in concentration. What was more amazing to see was that there is also a deficit of concentration here, right, further upstream. Okay? So this is a fairly robust thing in concentration field, so it doesn't show anything about the coherent structures just yet, right? So the next question we asked was, Okay, if I have a high swirl event away, because this induced velocity can come from a vortex that's up here. So we basically said if I have a vortex here, right, and goes back to the qualitative images earlier, right, how will my concentration field looks like, right? So these two fields are two independent diagnostics, so they do not talk to each other. There is no crosstalk between the diagnostics, right? But the moment I condition the fields with a swirl event, I see a high concentration event here, right? And I see like all the traditional things that that Adrian and Christensen had shown 25 years ago. What we also see is that we see the secondary concentration event again associated with, I believe there's a vortex here, there's a little bit of a vortex there, right? Across an inclined event. This, if you don't believe me, I wouldn't blame you, but you kind of see that this again consistently shows, that's why we're more confident on this thing. But the pattern that we see is if I have a swirl event, I also have correlated concentration events upstream and along an inclined interface. It kind of follows this, right? And it shows a compelling evidence that like even the velocity field, so these are known to have beta events in between, so that kind of have opposing shear layers, right? And they basically push the fluid apart from each other. So you get like a saddle type topology that we know exists, and it's nice to see that that's in fact the reason that the concentration is being organized coherently. So now I can state a lot more confidently that like what is the role? So there is actually a strong preferential arrangement of scalar that is also statistically significant. Okay. We did a few more things. We basically said, okay, if I pick the secondary blob, will I see the primary blob? And the answer seems to be no. So in other words, a strong concentration event here is not necessarily the action of a coherent packet. I mean, it could be an incoherent event. It means turbulent flow field, right? Different things can happen. Doesn't necessarily mean you'll have a strong high concentration event downstream up there, right? And so there are other breakup mechanisms outside of these coherent packets. It's not the only turbulence that exists, right? But if I pick a strong swirl event here, I do tend to see, again, there is a vortex and there is a blob here. So again, these are entirely independent events that we pick. So if I pick a strong swirl event here, I also see weak primary blobs, what used to be primary blobs earlier on. So what I want to say is if I have a coherent packet, they usually result in a high concentration further away from this. Right. So this was very encouraging. So at this point we were fairly confident. I'm not showing this here. We also just did brute force conditional averaging. We basically took the two events and then just looked at just picked the fields that have that thing, and we basically see the same structure. So it's not even dependent on the type of conditional average that you do. You just have other artifacts with that thing. So what I did was basically I said, you know what, like I want to see how and if this mechanism actually truly makes sense, right? So this was like one evening work, so not the most significant of this thing. This is a turbulent boundary layer measurements I took for my PhD, like I'm not close to 9 years ago now, 10 years ago. Right? Highly resolved measurements. So again, these are bandpass filtered, so you see what turbulent structures exist, right? And these are contours of swirling strength, so you can see that this is a vortex, and I kind of see the vortex there. There's one more vortex that I can also see. And what I did was, you know what, let me just seed particles continuously in a small region and see how these particles end up, right? Where do they end up? Right? Are these mechanisms there, right? And I'll let you be the judge. If I just track this thing, so this is just me tracking the particles, and I can tell you this, anytime there is a big blob that ends up there, right, far away, again, I'm injecting it here, the boundary layer is about 25 millimeters thick, right? You will see the same structures, right? You will see the same packet arrangement, right? I'll try to pause it, right? So if you pause it, you can kind of already see that this packet is taking this guy up, and then you will start to see this thing show up, right? Oops. So if I just let this play out, right, you can kind of see this, and you can kind of see many of these structures, like the inclined vortex structures and the uniform momentum zones. I've had great pleasure talking about these features. You basically kind of see as the uniform momentum zone builds up, they basically layer back, piggyback on top of the structures, break up, and end up being there, right? Okay, so the conclusions for this effort, right, were basically large coherent packets arranged at scalar in a coherent manner, especially immediately downstream, which can have long effects later on, right? But the most important thing is they were the primary mechanism by which the scalar reaches the outer layers of a boundary layer, right? We call this large meander events because this is important. If a high concentration blob reaches the upper layers of a boundary layer, it can get transported a long distance without dispersing, right? So this would be very important, right? And we kind of prepared a schematic that kind of integrates this paradigm with our existing understanding of the coherent structures. Like, for example, you get a uniform momentum zone, hairpin heads, like the features and the scalar blobs lined up with this. We just published this in a JFM paper that just came out like a few months ago, right? And we also looked at, like, if you look at these blobs and discretize this and track the center of moment of these things, right? Like how they occur, that typically predicted using a Gaussian plume model, right? So this is this curve that you can typically fit with. And if I do that, if I do the best Gaussian plume model fit for this thing, and you do see that on a logarithmic scale, you get these events, rare events of large deviations off the plume away from the wall, which I believe is the action of the coherent structures. So that was the outcome of that effort. Completely different in experimental effort and analysis, looking at atmospheric scalar transport of a point source, right? And I'll just take a full pivot on a different direction, where we look at unsteady flows, separation, and rough textured surfaces. Okay, so the motivation of this research, okay, and I'll tell you once I get some water. Oh, okay. Again, if you have a theoretical and applied mechanics degree, this is what an airplane looks like to you, right? So we have an airfoil flow going around it, and we have the boundary layer there. Aerodynamicists ignore it until they cannot ignore it, because if it separates, it alters the vehicle scale aerodynamics. So it actually alters the inviscid flow around it, right? So, and it can be unpredictable, sudden, hysteretic, all of those things. I mean, we have like more than 50 years of research on that thing, right? But the thing that we wanted to attack was everything gets worse in unsteady conditions. So if you have a gusty environment that your plane is going through at high angles of attack, it just makes that much more unpredictable. The other effect is the wing-in ground effects. If you have a plane flying very close to the ground or very, very close to the sea or high seas, you'll have the ground effects also make these much worse. So our effort was directed on understanding boundary layer dynamics in unsteady conditions that lead to separation, right? And when I mean by unsteady conditions, again, for a TAM person, I'm going to have a flat plate boundary layer, right? That's either subject to a mean pressure gradient or not. And then I can have a pressure gradient, pressure unsteadiness of advecting kind. So I can basically have, let's say, a free stream vortex that moves, or if you have like a winging ground effects, you go on top of a little hill, right? So that would be this disturbance on the lifting surface. The other thing is pressure unsteadiness of the global kind, where the pressure everywhere is changing in an unsteady manner, which is what would be happening if you have a pitching airfoil, right? And the goal eventually, right, is can we engineer textured surfaces to make separation more resilient in these things? So it's not to entirely prevent separation, but if you have unsteadiness, can you have a boundary layer that's better at dealing with it than a boundary layer that's like largely susceptible to this thing, right? So it's more on a separation resilience study. A quick highlight is I'll just present aspects of these things. This is very much in progress. So the first thing is like, okay, how do I first, in a very, very clean fashion, impose a pressure gradient of pressure perturbation of an advecting kind, right? We picked basically a vortex-like flow, right? So for example, if you have a vortex that kind of advects further downstream on a lifting surface, this is very similar to what we would have, right? And like we do this in a collaborative sense. So there is a team at Auburn University that does the aerodynamics of this. So they use a real vortex and an airfoil that do this. What we do is basically we take a translating rotating cylinder. So it's a span-wise aligned, it rotates and it translates just like the name would say it, right? And we want to see if this can be used as a surrogate of a line vortex, because again, this is clean and this is tractable, controllable, as opposed to a real line vortex. So we basically built that. We basically built a rotating cylinder, right, that can also translate, right? Okay. So that's the test section. And this is moving at some speed. This can actually move up to 8 meters per second, so it kind of gets pretty scary once it starts doing that. So we basically use a linear actuator to move a translating rotating cylinder. But the question is, does it behave like a vortex, right? To do that, we basically said, let's forget about turbulent boundary layer. It's messy enough as it is, right? And we basically said, let's just see if this can induce an axisymmetric flow in the frame of reference of the free stream, right? So in the frame of reference of the free stream, there is no flow. We built this. The cylinder can have a certain height away from the wall. So it's a vortex next to a wall. It can have some RPM, lambda, and some translation velocity c, right? And we basically did PIV that looks like this from the camera frame of reference. And we also put a microphone on the wall because we want to measure the pressure perturbation on the wall. And microphone on the wall would basically give you a pressure sensor like this, right? So these come pre-calibrated and they pick up all things outside of the pressure. So we filter it and we say that, okay, that's the pressure that's imposed by the cylinder. Okay. Going forward, I'm going to transform this time axis into space axis using a simple like an advection in the frame of reference of the cylinder. But if I do that, so basically minus c times t, this is what pressure will look like on the wall. Okay, so this is when the cylinder is on top of your pressure port. This is all upstream of the cylinder, downstream of the cylinder, and this is the span-wise direction. So we did this at multiple spans to make sure it's actually span-wise homogeneous. And this is, if I slice this, horizontally, this is how the pressure would look like. So before the cylinder, so imagine this pressure perturbation basically moves from left to right. So before the cylinder comes, there is no pressure, and then you get a low pressure, and then you get a slightly higher pressure, and then it recovers back to before what the turbulence was. And we take a span-wise slice and see that at least in the middle 100 to 200 millimeters, which is about 6 delta. This is fairly homogeneous, not too bad even at the edges, right? We did a whole sweep. Okay, the role of RPM. So if you increase the RPM, your pressure peak increases. Speed, we increase the speed. Different heights, so you can move the cylinder up and down. So closer the cylinder, like stronger is your pressure perturbation. So this is how P min goes with H. As the H increases, P falls down. Right. What we also did was we had the PIV velocity fields, and we didn't trust the microphone just yet. So we wanted to say from these PIV fields, I can kind of estimate the pressure signal by some pressure estimation, right? Like there are many ways of doing this. We did what's called as an omnidirectional pressure integration method. The really nice paper and a really nice technique. I would kind of recommend this. We were pleasantly surprised to see how well they agree with each other. Like they're completely different diagnostics again. They're only related to each other through Navier-Stokes equations. And the agreement looks like this for all the cases that we've studied. So we know that your microphone and the velocity information are capturing exactly the same information, right? And we said, okay, let's compare this. This is an ideal inviscid vortex. So we use like a Rankine vortex method of images. And this is what we see. Fairly axisymmetric, I would say. If I take a slice, this is the ideal vortex. This is my real vortex. Obviously, I have lesser negative velocity. So this is minus u. So lesser negative velocity because of the viscous effects than I would have if it was an ideal vortex. But the question is, I don't want this TRC to be a one-off thing. Can I actually relate it to my ideal vortex somehow through flow? Right? So we started the most basic of the things. We basically said we'll pick the U wall of this and U wall of this, right? So this is what we are interested in, what it does on the wall, and just normalize the velocity fields and see if we can establish some similarity. And so that's what we took. So both of them are, we take U wall. So this is the raw data. This is what the raw data looks like for different cases, RPM, lambda, all of those cases. This is what the theory looks like, right? And if you normalize these two with the U wall, they kind of reasonably collapse, right? So I'm talking about the velocity taken at all distances away from the wall, right? And if you compare them together, there are some differences, right, around 2h and negative 2h, but they're not entirely far off in their shape and form. Okay, there are a few aspects here. So there are some viscous aspects that I can get into if you talk to me later. We know why this deviation happens, and this deviation is very encouraging, right? If you look at the vertical slice, so from the cylinder further away, they also collapse. Obviously, close to cylinder, they would not collapse because they're like very different flow fields next to the cylinder. One of them has boundary layer, the other one does not. Right? But far away, if I normalize it, if I look at it in this region, they collapse fairly well. And if I'll take mid-plane between the two, and again, mind you, I'm all dividing them with the wall velocity. So if I divide all of them with wall velocity, they collapse reasonably well too. So they all show the same trends with some viscous effects topped on top of the experimental data. So we basically said, like, we can establish these things, and I can actually, for any combination of operating parameters, at least in the span we checked, you can basically take the inviscid flow field, scale it literally, and we're trying to get a more hydrodynamic version of this thing. If you scale it, this is about half, more or less, right? Scale it literally, and it would end up working reasonably well. So the thing that we wanted to take out from this is this TRC mechanism is a fairly good representation of an inviscid vortex moving in the free stream, in the frame of reference of a free stream. Right. The last thing, I'll again quickly zoom through these things, okay, in the last 5 or 7 minutes that I have. Okay. That was good. Then why did I say, why are we doing this? We basically want to do separation control by using textures. I won't get into too many details here, but the way I define textures is, it is roughness if I didn't create it, it's textured if I created it, quite literally, right? If I kind of say that this is the skin friction profile on the wall, and I manufacture it, then it's texture. Right? But both of them will basically have inhomogeneities in skin friction that will then, this is span-wise wall normal plane, that would then have high momentum here, low momentums over regions of high skin friction. So you can use skin friction to weakly control the momentum on a flat plate boundary layer. And our idea was, well, can we use the same strategy to to control the separation. There is a reason we felt this was a viable strategy. Again, I don't have time to get into that, and I would be happy to talk to you about more. Like, what hydrodynamic argument do you actually say that this could be a viable strategy? But what I would like to show is that you can use this, and it's showing actually a response, right? And the things I want to focus is these textures are very, very small, right? So if you look at the riblets, this is the boundary layer. The riblets is here. Right? So this box is entirely fit in there. So these secondary flows are not structure-driven flows. They are skin friction imposed inhomogeneities in boundary layer. Right? And if we lay such a roughness panel on top of a flow, so flow is from left to right, and then it kind of just separates. If we lay such a skin friction surface and look at that separation, all I want to tell you is this is the smooth wall. This is the divergence. So this region has higher momentum, right? This region has lower momentum. So this is two planes in the spanwise regions with the high and the low momentum regions in the spanwise. And they're about half a delta apart, but the turbulent kinetic energy is about 25% different, right? So the boundary layer inhomogeneity is weak, but the moment you subject it to pressure forcing, it amplifies everything, right? So this was the preliminary data. We are doing a lot more sanity checks on this thing and making sure that what we see is not an accident. My student basically he went to town with this. We basically got this 4-camera high-speed particle tracking system. And I'm showing 2 planes here. On top of that ramp, but it's basically swept like with 8 planes. We have like a full 3-dimensional representation of what's happening with the flow. He's still processing it because there's about 200,000 vector fields taken at 6 kilohertz. But if we do a short average in the spanwise wall normal plane, the contrast is not very clear. But this is a blue blob here. There is a blue blob here that represents flow inwards. So the flow is coming out here. This is the reversed flow, and we see that it is spanwise inhomogeneous, where you have high momentum pathways, which is the weak regions where you have relatively high momentum. You have stronger attachment, and low momentum, you have weaker attachment of the boundary layer, right? And at the minimum, what we could say is that we have localized separation differentially. So we have a spanwise differential in the stability of the boundary layer to separate. Okay? So that brings me to the conclusions of this thing. Like, I've covered a lot of those things, right? So we basically said for this part, TRC can impose pressure perturbations. I did not get into this. This is basically imposing pressure gradient by wall aspiration. Another crazy system that involves about 400 fans that you control with a computer, right? And we have shown that the separation can be influenced using textures. Why, we don't know. Like, we have data to kind of look into this. We have efforts on a much cleaner flow to give us more information on what turbulence is doing, like how is this cascade working. But I hopefully will have answers for these things in the next year or so. Okay? So that's an overview of the work. 3 different forms. Like, I hope I have covered systems development for flow control, turbulence separation, and scalar transport in boundary layer, like I promised early on. Like I said, this is all the work of my PhD students and master's students and undergraduate students at ASU. So thank you very much, and I'm happy to take questions on any front.
Thank you. Thanks a lot. Any question from the audience?
I think Judy has a question.
Yeah, very beautiful work, very impressive. I'm just wondering if you consider the advection of the coherent structure and then for your first work,
yeah,
and do a like spatial average. How much difference would it be to like resolve this coherent structure and estimate the dispersion versus just simply use some semi-empirical equation to estimate the turbulent dispersion coefficient? Like how much difference would it be?
So if I understand your question right, it's like, so the coherent structures, so we don't have a time resolved data of this thing, so we only have snapshots.
Yeah.
Right, so they're either there or they're not there, and we don't have a time history of how it got there, right? So it's very hard to do this in a spatially averaged sense, because you will be averaging across different mechanisms of transport. So sometimes it's the hairpin packets that are doing this transport. Some other times it could be something else. So if we want to selectively isolate the mechanism, we need some selective process. So I think with the temporal history, we can do a little bit more by using Taylor's hypothesis and some growth theory. But I don't know if we can do it with the data that we have. Right? Does that answer your question?
Yeah. Do you think you need to do like a lot of like multiple experiments and then get a steady state? Because if you simulate it at different time points,
yeah,
you will have different coherent structure.
Yes. So no, you're absolutely right. The coherent structures would be different. The age of the coherent structures also matters. So this will be a very complicated function of like what was the initial coherent structure that first started interacting, right? And like you said, it grows and it kind of convects and it advects the fluid around. So there is a Lagrangian, so this is the way I look at it, is this is the Lagrangian effect of the coherent structures. So I think FTLEs is probably a good way to look at this thing to describe it, but I haven't done that yet.
Yeah. Thanks.
Thank you. Any more?
Yeah, thank you for the nice talk, Professor. Yeah, I have a question regarding, so when you show the conditional averaged, so when you averaged based on the concentration, it didn't show other events, the adjacent events, but for when you average over this world strength, it showed the vortex events, right?
So it showed the vortex events in both, right?
No,
oh, you're talking about the vortex events?
Yeah, vortex events compared to the concentration, averaging based on the concentration. I'm still trying to understand why that was the case.
So this one?
Yeah, this one, and then I think this is average based on the swirl strength, right?
This is average based on concentration.
Concentration,
yeah.
Okay.
So this showed the three blobs,
Okay.
right? And this is the average based on the swirling strength.
Right. I think the next slide you showed averaged based on the concentration for the second blob.
Oh, yes, this one.
Right.
Give me a second. Yes, this one.
Yeah, I'm trying to understand why it did not show the further event.
So this other event, it's being drowned in the occurrences. Mm-hmm. So sometimes this blob occurs with another blob there,
right.
But that's not the norm, right? That's more of an exception, right? That's what this plot shows, at least. This basically shows that if it occurs here, sometimes there is a concentration event there, sometimes there is not. Right? So this correlation is not obvious. But what it does show that an event occurring here normally, or at least more probably than not, has a concentration event here. Right? So there is both a coherent and incoherent mechanism, but coherent mechanism always results in that, was our interpretation of this.
And is there any statistical measurement of how separated these blobs are? Is there any
That's a good question. So the problem here is we only have one Reynolds number, because this was originally meant to be a diagnostic proof of concept and development. That is definitely something, because it will be a function of delta and the Reynolds number. Right, so that's something we have to look at. We did do a raw conditional average, and we presented it in the appendix of the paper, where we picked like at this delta vicinity. So you have a concentration event, and in this vicinity there should be a swirl event, and that's my event, right? And that gives you a bit more information on this. But yeah, we need to look at that.
Sure. One last question. So this increase in the height, is it proportional to the boundary layer thickness? Or is it like a fully developed turbulent flow, but still these things, the increase in the location of these coherent structures, can it be obtained from some kind of advection diffusion arguments?
Yeah, I think if we go to this video, right? This tells you. So it's usually related to how far this vortex can go. Like some of these vortices are like of the order boundary layer thickness, right? Maybe if I go much further downstream, they might end up further out. They would obviously be more diffuse.
Right.
We don't know that, but given that this vortex is here, probably it will get there.
Okay.
Maybe in more diffuse manner.
Okay. Sure.
Yeah, it's a good question. I don't know.
Thank you.
I'm giving to Jerome, but I had one question related to this, so I'm taking that a little bit right away. Back in the days, we discussed a lot about the spacing between vertical structures, whether it's viscous wall or it's delta, right? So you're normalizing everything with delta here.
Yeah.
Is that like a 50-50 chance, or you thought about it?
I have not thought about it, right? But the thing is, the Reynolds number here is about, RE tau is about 900. So we usually have like at most one hierarchy, like one hierarchy of vortex structure. So the spacing, no, we have not scaled anything in the horizontal direction. But that's, now that I think about it, that's probably a good idea to look at that, because different heights, they would be closer or further apart.
Yeah, thanks for a nice talk. I have a couple questions. One is related to the design of this sort of the passive scalar transport experiments. It feels like you view this passive scalar as some kind of fluid particle advection, right? In your experiments, all the arguments you are making is including this video, is trying to use fluid particle motions to argue how the scalar is going to be transported in the flow.
Yeah.
Is that correct? So in the actual experiment design, when you inject a plume, and a plume may have different fluid properties, right, in terms of viscosity or the buoyancy, and I'm just trying to understand how do you reconcile the actual discrepancy between the fluid properties in your experiments with the argument you're trying to make to think this is a passive scalar transport phenomenon.
Yes, so right now, this is really only valid for passive scalars. If we induce, like, let's say, buoyancy, right? So now you would have two competing mechanisms, right? One mechanism would try to advect it
So
up.
that's what I'm thinking, because when you inject that methane, right, for UV and generating fluorescent light, so that fluid has different properties compared to your, main fluid, and so the differences between the fluid properties will cause some discrepancies between, your current arguments with what you're going to see in the experiment. How that has been taken into account in making such argument.
Absolutely. So I do not think this would directly extend to like buoyant plumes at all. It would be nice to see how this works out, because now that we can do it, like I said, it's more of a development to be able to do strongly buoyant plumes. But if I were to guess at this stage, we would basically have like an advecting, if I have to come up with names, like an advecting time scale and a coherent dispersion time scale, and then there is a buoyancy time scale. So I'm guessing at some point, like, buoyancy will be the most dominant effect, and none of this would actually
I think
matter.
there's some dimensional arguments you can make, right, by looking at the fluid property differences and also your turbulence scales.
Yeah.
The second question is related to the experimental setup you showed at the very end. I think is that dual plane PIV setup, like you're doing stereoscopic PIV on two parallel laser planes?
You're talking about the scalar transport?
The very last video you showed this 3D particle tracks.
Oh, this one. No,
Yeah.
this is done separately. This is done at different planes.
At different time? Or?
Different times,
Oh, okay.
Yeah, they're not simultaneous.
Oh, it looks
this is
like
not
a parallel
simultaneous.
planes. Okay.
Yeah.
Right. Yeah.
I would need 4 more cameras.
Yeah, that's why I was
something
curious
else, yeah.
because I remember there was some point you have this parallel plane. People are trying to resolve 3D flows, and they're resolving. They do stereoscopic PIV on two planes. They can calculate velocity gradient. But eventually that was kind of completely replaced by the tomography. PIV. So this is like two different planes.
Yes, this is 2 different
times.
experiments. Yeah.
But you're using 4 cameras looking at one plane.
Yeah. So this is a volume. So this is actually.
It's a very thin, you're still doing tomography PIV, but for very shallow.
Yeah. So this is the shake the box thing that they have. So we are doing both.
Okay.
Partly because I was not entirely confident with shake the box working well in air.
Okay.
But I was pleasantly surprised on how well it works. But there are some limitations. I mean, I can go on and on about that. I do think Tomo PIV is a better way to go with this if we don't need the time information. But we're processing both with the particle data that we have.
All right, thank you.
Thank you very much. Well, we are at 4:10, so let's thank the speaker again. And you can take.
Okay. Thank you.